That should be fun. This is a presentation of gravity as a gauge theory. It's a very particle physics-y way of thinking about general relativity. You know, if you read all the relativists, they all talk about here's a manifold and here you're moving on this manifold and all this geometric. There's none of that here. This is just like what we're going to do is we're going to gauge Lorentz transformations. We're going to make Lorentz transformations. So Lorentz transformations are, x mu goes to x prime mu, some lambda mu nu, x nu. We're going to take this and make that a local transformation. Okay, that's what we do for a lot of our. We have a global invariance. You make it a local invariance. You pick up a gauge field. You get a little Lagrangian. You get dynamics. Interesting stuff comes out, and that's going to turn into gravity. Okay, it's a little bit puzzling at the start why that should be gravity. The best I can do as motivations. I mean, we can just do it and see what it is, but the best I can do as motivations is the equivalence principle. Okay, if you have the equivalence principle in picture-wise, okay, if you have a little Einstein elevator, you put a little cartoon person in this guy, and you accelerate it up, that's locally equivalent to having a big mass beneath it. You're sitting in here, you feel the same gravitational fields. Okay, well, the left-hand side then would be described by a Lorentz transformation that depended on time, space and time. To describe the acceleration, you can't just do a boost, you have to do a boost that keeps changing with time. Okay, so that's, maybe you can get a little out of that. Or the other equivalent is, of course, the free fall. If you're free falling in a mass, and compared to just sitting in an inertial frame, there's again an equivalence between a local Lorentz transformation and gravity. Anyway, so that's enough for motivation. Okay. I do need to do a piece of technology. So what I'm going to end up doing is I'm going to end up going through Lorentz transformations of fermions. So let's just do a straight Lorentz transformation. Okay, so we want to keep we'll have, again, x mu prime is lambda mu nu, x nu, but psi is also going to have to get transformed. So psi is a four-component vector. So we're going to have psi prime of x prime equals some s of lambda on psi. Okay, this is a 4x4 matrix. Okay, and what you know is that if you just know what a spinner looks like, you know that if you change frames, that spinner is going to change. There's an upper component, lower component, depends on momentum. If I boost that, the momentum changes, so the spinner indices change. How does it change? So if you want the Lagrangian to go to Lagrangian prime, x prime is, Sidebar Prime, x prime, I gamma mu d mu prime minus m, sorry, prime of x prime. This is then psi I want sidebar gamma 0 S dagger gamma 0 and then I have I gamma mu d mu prime minus m f. Okay. If we're going to do this with gamma 0 S dagger gamma 0 is S minus 1. That's required for the mass term to be invariant. Okay. But then you also have a condition on the gamma matrices. We need then S minus 1 gamma mu d prime mu f is gamma mu d mu. Or if you go back to the Lorentz transformations, it's S minus 1 gamma mu lambda mu nu f is gamma nu. Okay? That's, if I go back, put in x and x prime in terms of lambda, that's what I need. Okay, so there's my condition for the invariance of the Dirac equation. And the easiest way to do this is to write lambda mu nu infinitesimally is g mu nu. Well, that's actually delta mu nu. One upper, one lower is delta, plus some omega mu nu. So this is now infinitesimal. Okay. The condition that lambda mu nu lambda nu sigma delta mu sigma, that's the condition of Lorentz invariance, that if you just work at it a little bit, do this expansion, it tells you that omega mu nu, at least if I put the upper and just everything upper, is antisymmetric. Okay. And it's real. Okay. So there's a condition there, and there's a bunch of algebra that were set up. Let's just so this is the let me skip all the stuff and just give you the answer. I have a bunch of calculation here about it. It is that S is 1 minus I over 4 sigma mu nu omega mu nu. Okay? That's the piece that that satisfies the above equation. Okay, and the calculation just is a bunch of commutators here and there, and you just do all these commutators out. But in a sense, it has to be. It's almost obvious, because if this is antisymmetric, this is some combination of Dirac matrices that's antisymmetric. There's only one combination of Dirac matrices that's antisymmetric. It's either this. The only thing else it could be is epsilon mu nu alpha beta sigma mu nu. Okay, so that's an antisymmetric combination. Okay, remember sigma mu nu is I over 2 gamma mu gamma nu. Okay, and then to get a finite transformation, you take S as you do a bunch of infinitesimal ones. An infinitesimal one might be 1 minus I over 4 sigma mu nu omega mu nu over n. So if I make up one big transformation with n small ones, I would have that as my transformation matrix. So I have one finite transformation made out of n infinitesimals, and I take the limit n goes to infinity, and this just exponentiates. This is e to the minus I over 4 sigma mu nu omega mu nu. So there's the description of a Lorentz transformation for a fermion. Okay. Anyone have questions about that piece? No. So let's now start talking about local Lorentz transformations. Okay, so we'll take that form, and we'll let x prime is mu is lambda nu of x nu. Yeah, this really can be any function then at all, really. And let me start with a scalar field. So phi of x is going to go to phi of x prime. That's the scalar field transformation. The action that we would start with is integral d for x g mu nu d mu phi d, that's a half there, d nu phi minus m squared phi squared. And so if I just make this transformation, this would go into, well, it'd be integral d for x prime dx prime determinant. Here's the Jacobian of the transformation. And this would be then g mu nu. Yes, so it's d x prime dx mu d x prime dx nu d prime, that's alpha phi d prime beta phi beta. Okay, so I've made the transformation there, and now I've got my primed, written in terms of primed variables. If we want that to be an invariant, you can see we have to do a couple of things. And the obvious thing that we're going to have to do is, so normally under usual Lorentz transformations, this is an invariant, and that's an invariant. So that's the Jacobian of the Lorentz transformation. Usual Lorentz transformation is 1. And g mu nu is an invariant. Okay. But here, if we're being completely general, it can't be. So we're going to end up, of course, promoting g mu nu to a field. So it's a field, and giving it some transformation properties such that well, if we take g mu nu of x goes to d x alpha dx prime beta mu. Actually, I'm using some old notes here, and I caught a mistake here somewhere in this area here. So there's some potential for being a little screwed up on some index. So don't trust it perfectly, but the concept is, of course, right. G alpha beta. Yeah, I've got my indices. See, here's one of the places where I've got my indices up and down a little bit differently. X beta, X prime. Anyway, that's what my notes claim. Sorry. Okay. Yeah, the downstairs is a prime, I think. Well, it's a scalar. So but when you do it, that's right. So when we do a transformation of the fermion, which I'm going to do next, it's going to have a piece, but the scalar doesn't. Okay. And the Jacobian, if we define G as minus the determinant of G mu nu, this guy transforms like G goes to dx prime dx squared G of x prime. Such that the volume elements, d4 for x square root of G goes to the integral d4 x prime square root of G prime. Okay. So this is the standard construction. Then the invariant action is then just S is the integral d4x square root of G of x G mu nu of x d mu phi d nu phi minus m squared pi squared. Okay, so that's the usual promotion of the metric to a field. At this stage, I want to introduce the vierbein. V A mu. Okay, and the vierbein can be, by the principle of equivalence, you can always locally go to a flat metric. You can change your coordinates that G mu nu, which is a function of x, by choosing some new coordinates. So the new coordinates will be, I'll call them CA, or zeta, CX mu, CB, DX nu, A to AB. Okay, so this is the flat metric, and the principle of equivalence tells us that by changing our coordinates, we can go to a metric that's locally flat. And so if I use the coordinates z or zeta, those are the coordinates for which I appear locally flat. But then, doing that, I can define then this vierbein, VA mu of x, is the field that's defined by VA mu. Okay, so this is now going to be a field at each point in space-time. There's a field that this defines. Okay. This has the transformation that V a mu of x goes to V prime a mu of x prime, which is dx prime nu dx mu dA nu. Okay, so it transforms with one of these transformation functions. Okay. My usage is going to be, I'm going to use always the A, B type of indices for flat and mu, nu for real coordinates. So, okay. If I do this, then the square root of g is just the determinant of v. So it's just the determinant of that guy. So it's the square root of g, basically, right? So this is the square root of the metric. V is the square root. And I can define a covariant derivative for scalars so it'll be dA is VA mu d mu, sorry. Okay, so A and B indices are raised and lowered with etas, the others are raised and lowered with g's. Okay, such that the Lagrangian now is eta AB, derivative A phi, derivative B phi squared. Okay. So there I've got a covariant derivative for a scalar. Okay. Let's do a fermion. Okay, here's where things get interesting. Okay, so I'm going to do this for infinitesimally. So basically, x mu is going to be x prime mu is going to be x mu plus some small one with a mu is omega mu nu a nu. I'm sorry, I want that to be x. This is lambda mu nu. X nu is delta mu nu minus r plus omega mu nu x nu. Okay, so that's the thing we have there. So we have this coordinate transformation, but we're also going to then require psi prime is going to be f of lambda psi, which is 1 plus 1/2. Okay, I'm going to define this notation SAB here. SAB is let's see, do I have an I there? Let's just go back up and check. Yeah, this has something with an I in it. Yeah, it's minus I over 2 sigma AB. Omega AB of X. Okay? One of the things that you just saw I did, so this is the transformation we had before. One of the things that we just saw that I did is I put Minkowski-like indices on the gamma matrices here. They aren't coordinates. So these are just things that are summed over. They're summed over using the Minkowski matrix. So in this type of transformation here, they're not the same as a coordinate. The gamma matrix doesn't transform the same way as the derivative does. Okay, it's just a matrix. So I'll carry those along as a separate transformation, as a Latin index. Okay. So we have a task ahead of us is now to make the Dirac-Lagrangian invariant. Okay, so we want L goes to L prime, which has two pieces. There's two pieces that we have to work on. There's Sidebar Prime I gamma A, okay, it's gamma A D A, but actually that's not really an A index. So let me do the following. Let me give you the answer here rather than beat around the bush on it. Is we need to put in this vierbein field here, V A mu D mu. All right, so if I put in put in the vierbein, then this piece becomes an invariant when we do the transformation on the vierbein. So with the V mu A is the whatever I had up there. Let's go back up and see it. Dx prime. Okay. So if I do that, then the derivative pieces become invariant. All the interesting work. So that's really just a continuation of what we were doing before. The square root becomes the square root of g and the integral d4x keeps that invariant. This piece becomes invariant. All the action now comes in this, what it will call the spin transformation. So let's just work on the spin transformation. Okay. We have Psi prime is 1 plus 1/2 omega a b s of x SAB psi, okay, which is this f psi. That's the infinitesimal version, and we know how to get the finite one. The Lagrangian prime is then Sidebar s minus 1 I gamma a v a mu d mu minus m f. So the mass piece is invariant, but the derivative piece now is not going to be invariant. There's going to be a derivative on omega mu AB SAB. That's not going to be invariant. So what's the answer? The answer is, of course, you have to add a new gauge field. Okay? So we're going to now add a new gauge field. It'll be A B mu. So the mu is because it's going to go in a covariant derivative with the derivative. So the mu index is like the derivative index. A and B are going to be Dirac-like indices, so they're going to be flat. Okay, so the derivative, the covariant derivative, is going to be d mu plus 1/2. Again, SAB is that sigma matrices, A B mu. Okay, which, and actually, sorry, I guess I also need my little vierbein. So this is dA mu A. Then this has to be, these indices have to be rewritten as CD. Sorry about that. Okay, so this is the piece that we had for the scalar didn't have the spin part of this because it doesn't carry any spin. So sometimes this gets written as V mu A G mu plus A mu, where this is now a matrix. Okay. Okay. Well, the trick now is to choose the transformation property on A such that we get an invariant. So our Lagrangian to start with is then going to be Sidebar gamma A dA minus M psi, and we're allowed to choose the transformations of A to make this an invariant, just like we did for gauge fields. Okay? So the transformation properties, okay, for this Lorentz, this small transformation, V A mu prime is V mu A plus omega A B V B mu. Okay. and A prime mu is A mu. So this is the matrix field plus 1/2 omega AB SAB commuted with A mu. And then there's a piece with it that's my notes say -1/2 SAB d mu omega AB. Okay, but that's, if you go back up here, you can sort of see where these terms come from. There's, to make this an invariant, I have to cancel up the d mu omega. I also, since now I have a matrix field here, I have to make the, so that it has the right commutation properties with the gamma matrices. And this is what works. Okay, this is pretty similar to Yang-Mills. If you think about Yang-Mills, there's when you do a transformation on a Yang-Mills field, you get the field, you get, let's say it's SU2, it's epsilon ijk, a commutator piece of tau with A, that comes out there, and then there's a piece that's the derivative. Okay. So without going through all the algebra on that, this allows L prime to equal L. Okay. So now we've got ourselves a new field. So, okay. Okay, so we have an invariance and we have a new field, and then we all, if we're just thinking of this as a gauge theory, the next step is to find a Lagrangian for this new field, the A field, that is also invariant and gives the Lagrangian for it, the dynamics to it. So let's go back, and so now we're on our pathway to the Einsteins. So now the action for the new field. Okay. Okay, let's just recall how we did it for gauge theories. So in Yang-Mills, we had d mu, which was d mu minus I g a mu. A mu would be, for SU2, let's say, is tau I AI over 2. If we take the commutator of two of these, d mu d nu, that's the commutator of 2 taus is also a tau. That's fi mu nu with a minus I g. This ends up telling us that f mu nu is d mu a nu minus d nu a mu plus g epsilon I j k a j a k Okay, and this guy comes from the commutator A with A. Okay. So now let's repeat it for now. So just repeat the same construction. Okay. I've got d mu, which is d mu plus a mu, with a mu equals 1/2 SAB, AB mu. So the indices AB are like the index I, so the matrix instead of tau I is SAB, but that's okay. So the obvious thing to do is to imagine taking d mu with d nu. Okay, that's something. It's going to be proportional to SAB over 2. Okay, from the Dirac piece. It then has two indices that are mu and nu, and it has two indices that are A and B. Okay, so what is it? If you just do it, then R A B mu nu is d mu A B nu minus d nu A B mu plus A C mu A B, I want CB nu minus A C nu A CB mu. Okay, same structure as Yang-Mills. The two A's in an antisymmetric combination. So C is raised and lowered with eta AB, not G mu nu again. Okay, so there's our field strength tensor for this new field. So at this stage everything is parallel to what we did. Then in Yang-Mills, the next thing we did is we tried to form an invariant out of that, and the invariant, there's some normalization, was F A mu nu, I mu nu, F I mu nu. So you summed over all those indices. Okay. Here we actually have an easier way to make an invariant. So you could make an invariant the same way. You contract two of them, but there actually is a first order. So here's the difference. If we take the following, we take V A mu V B nu R A B mu nu. Then since we've followed our transformation properties all along, this is an invariant. And we don't have to go to second order. Okay. So our acceptable Lagrange density for gravity is some constant times r, which is 1 over 8 pi gr. And then you, of course, could do RAB mu nu, R AB mu nu plus R squared terms also works. So this is our first difference. let me just then show you how the things hang together. Right now, so the Einstein equations. Okay. At this stage, in this construction, we have two independent fields. We have the vierbein, the a mu of x, and we have this field, this gauge field, which is a b mu of x. Okay, at this stage, they're independent fields. This guy is typically called the spin connection. Okay, because it came out of the spin part of the action. Okay. So let's just write out the action integral d for x. There'll be this minus 1 over 8 pi gr plus eta ab covariant derivative of a of phi, covariant derivative b of phi, okay. Okay, so there's our fields. If I vary, this guy has v in it, so right now I'm not doing the fermions. This is just the scalar. This guy has v, and it has one power of a. Well, actually, it has two powers of a, but it has v and a in it. Okay, and sorry, that's right. So there's two powers in there. When I vary it, there'll be an equation that has one power and an equation that has no powers. Right? A and a squared. So when I vary with respect to a, okay, I get the following equation. So it only comes from the gravitational piece. A b mu is g. All right, I have rho sigma v rho a. The derivative with respect to mu of v b sigma. Okay, and g is vv. Okay. Okay. So this is the equation that ties the fields together. Okay. V okay, so A is now expressed in terms of derivatives of V. Okay. If you modify it slightly, so if I take A, B, let's put a lambda there, and I multiply it by VA mu, VB nu. Okay, that guy now only has the space-time indices in it. The A's and B's have disappeared. That's gamma mu nu lambda. This is the usual affine connection. Okay, so that's something that you end up seeing in usual and general relativity. This is the beast that you normally see, and it's come as one of the equations of motion. Okay. The second equation of motion then comes from varying V mu A. Okay, and then there's some work to play with it in terms of converting all these indices, the A and B indices goes to mu and nu type indices, just by multiplying by the right powers of z. That turns into r mu nu minus g mu nu r equals 8 pi g t mu nu, where this is the t mu nu is the 2 times the derivative of the scalar Lagrangian with respect to g mu nu. And this r here is g mu sigma v lambda a v sigma b, sigma there, r a b lambda sigma. Actually, no, it's lambda nu, sorry. Okay, so it's also constructed out of our previous field. Okay, so there's the Einstein equation for okay. So, interesting little construction, all of it gauging the Lorentz transformations, the affine connection that arose from the spin connection. We did this first order formalism where we have two fields, we reduce them by two, turn it into a single field by one of the equations of motion, tying them two together, and then up with Einstein's equation. Okay, so very particle physics-y derivation of this. Okay, what I'm going to do, I'll come back clearly and talk more about this later, but just right now